Welcome to Quadratic Applications. So in this video, we're going to focus on applications that involve quadratic functions. So we're going to look at maximizing things and minimizing things and really overall how we want to start to think about these types of problems. So let's get started with an example. Okay, so a farmer has 2,000 yards of fence to enclose a rectangular field. So first of all, let's take a look at the picture. So we have this rectangle. We have labeled width and length. We also have a definition for the function. So we have this function for area, A, of the rectangle in terms of length L. So we've also built this A of L function. So negative L squared plus 1,000 L. We have a picture of what that function looks like, and then a couple of different questions that we're going to consider. So really what I want to focus on, and the first things I think you need to think about when dealing with this kind of problem is, okay, what does each point on the graph represent? So let's think about what is the input, what is the output, and how do I want to think about each point on the graph, right? Because we know that input is what we generally consider the x coordinate to be, and the output the y. So within the context of the problem, right, this is our input. So L, or length, is our input. And the output is what? A. So the output is A, or area, of the rectangle. So that means every ordered pair on the graph is telling me a specific length and then the area of the rectangle that would be associated with that length. So for the first question, letter A, we're focused on the point 200, 160,000. So that's this point right here. So if I'm considering that point, 200, 160,000, what does that mean? So that if this is length and this is area, that means when the length of the rectangle is 200, the corresponding area would be 160,000 yards squared. So think about, we can easily see that, but when we look at the graph, but we can also see it in these other representations, right? So if I think, okay, L is 200, so if the length is 200, that means this length would also be 200. If I totally have 2,000 yards, then that would mean, okay, so there's 400. So subtract that from 2,000, I would be left with 1,600 yards to split between the two widths. So half of 16 is 8, right? So that means the widths would have to be 800 yards. So if I'm thinking about the area, which is length times width, then I would have 200 times 800, or 160,000. So I can see that information when I look at the diagram. I could also see that information if I just plug into the actual function definition. So if I want to know what the area is when the length is 200, I could also find A of 200, which would be negative 200 squared plus 1,000 times 200. So this will also give me 160,000. So let's consider the next one. What is the area of the rectangle when the length L is 600 yards? Whoops. Okay, so let's consider that. I'm going to grab a different color. All right, so if the length is 600, that means the I'm looking for an input of 600, and I want to identify what the corresponding output would be, because that would tell me the area. So let's see, if I look at this point, I can see the corresponding output is 240,000. And again, I could also see this the other ways. We could also see this by finding A of 600. And I could also see that by, again, kind of playing around with the diagram, right? So if I said, okay, L is 600, so if this is 600, then this would also be 600. So together that would make, what, 1,200. So I would have, if I subtract that from 2,000, I would have 800 left, which means that would get split between the other two sides. So altogether, the perimeter is 2,000, and the area would be 600 times 400, or 240,000. And again, that's area, so we would say yards squared. So now think about part C. So part C is actually asking you, what is the width? So what is the width of that rectangle with a length of 600 yards? And so really we've already answered that question, that we're not necessarily seeing overtly on the graph, but because, again, thinking about that same point where the input is 600, because we know that the length is 600 and that corresponding area is 240,000, since we know that area is equal to length times width, I also know that 240,000 is equal to 600 times the width. And so one way to determine the width would be just solving that equation. So that would be 400 yards. We also thought about that by playing around with that diagram and identifying the existing length and knowing that the perimeter was 2,000, and we kind of reasoned it that way as well. So there's always multiple ways to think about these things. What's important to me is that you understand how they're all related. The picture, the function definition, the graph, and how to interpret those things. That's what I think is really going to help you understand the applications. So let's move down to the next. So part D, when we look at the intercepts. Okay, so thinking about the x-intercepts. All right, so that would be this, and we have two of them. So 0, 0, and 1,000, 0. So with these things in mind, what does an x-intercept of 1,000, 0 mean within the context of the problem? So that, again, is giving us length and area. So when the length is 1,000 yards, we have no area. And again, think about it, that makes sense. If I only have 2,000 yards, and if one side is 1,000 yards, and that means the other side would have to be, that takes up all of the fencing that we have. We wouldn't have the other two sides. We wouldn't have a rectangle. So that's why we would yield 0 area. Similarly, if we consider the point 0, 0, we would fall into the same thing. If the length was 0, we would have no rectangle, so it makes sense that the area would also be 0. So if we consider some of these points like part E, where you have a negative involved. So if we look at this point, so where we have 1,020 and an output of negative 20,400, of course that doesn't make sense. We know we can't have a negative area, right? So once those input values or lengths go beyond 1,000, we end up with this negative area, because again, that doesn't make sense. If I have a side length that is 1,020, and that means the opposite side would also be 1,020, I have already used more fencing than I have. So really, that points to this next question of part F, when we're talking about domain and range. So when we're talking about domain, if it's without the context of this problem, we know that the domain of a quadratic function is all real numbers. But within the context of this problem, only specific input values make sense. So we're really focused on this piece of the graph. So those are the only points that really make sense. When we have input values that are between 0 and 1,000. So the domain is going to be 0 to 1,000, and we'll not include those endpoints, since at 0 and at x equals 1,000 we wouldn't have a rectangle. And the range, again, we only want positive numbers for the range. So we would go from 0 to the largest output or area, which is 250,000. So I'm not going to include 0, but I will include 250,000. So the last question, and this is typically what's asked in these questions. So here we're going, okay, what is the largest possible rectangular area? So if I'm being asked for the largest, I'm focusing on that vertex point, because that's going to tell me the length that is going to give me the largest area. So when I'm focused on that vertex, so again, that's 500, 250,000. I can see what is the largest possible rectangular area. So that would be the max area, which would be 250,000 yards squared. And what are the dimensions, the length and width of that largest area? So we can read the length off of that point. So the length that yields that area would be 500 yards. And then to determine the width, again, we have a couple ways we could go about that. One would be dividing the area by the length, right? We talked about that over here. So 250,000 divided by 500 would be 500. Another way to think about it, we could kind of play around with the rectangle the way we had with some of the other questions. So other things we've talked about, right? We could have taken this if we didn't have the graph already, and we could have completed the square and identified the vertex that way as well. So again, these are all things that we've talked about in previous lectures, and now we're really just putting them all together. So I think a lot of the work we're going to do with applications really comes down to the interpretation piece. So let's consider a couple more examples, and we'll do that here in the next video. Thanks.